Here we are again with a clip, a little snapshot of the geologic map of Virginia. Here we're looking at the boundary between the Blue Ridge province over here in the northwestern half of the slide and the western Piedmont on the southeastern half of the slide. Here you see Fluvanna County, Buckingham County. This is Albemarle up here, Nelson County over here, county line here. And here's the James River. Not that easy to see, but it flows through here, reaches its northernmost point here at Scottsville, and then heads down toward Richmond in this direction. But these are the rocks of the western Piedmont or the Potomac terrain. Here's the big Chapawamsek Fault. So this is the Chapawamsek terrain here. This is the Arvonia belt here, the Arvonia syncline. And in the eastern Blue Ridge, we've got, the Blue Ridge basement complex over here, and then the cover rocks, the sedimentary and volcanic rocks that lie over the Blue Ridge. But the boundary between the Blue Ridge province and the Piedmont province is this fault system coming down from the north. This is called the Mountain Run Fault. And coming up from the south, I think this is called the Red Oak Shear Zone or something like that. But anyway, it's the boundary between the Blue Ridge and the Piedmont. And sitting right on that boundary, just as on many of the major faults east of the Blue Ridge, we have a Triassic basin. This sort of teal, greenish blue color here is the geologic map of the Scottsville Triassic Basin. And we can see here that it pretty much straddles this fault. And it's filled. It's a basin that's about 200, a little over 200 million years old, 250 million years old, and it's full of sandstone, shale, and conglomerate. And in this particular Triassic basin, those rocks are largely red in color. When we talk about the geology of the Piedmont, of course, we often talk about tectonic plate collisions and the assembly of Pangaea and Appalachian mountain building, but the fact is, one of the biggest tectonic events to ever affect Virginia was post-Appalachian, the post-assembly of Pangaea. It's actually the breakup of Pangaea, the opening of the Atlantic Ocean, and the rifting and collapse of the eastern North American continent. And when that happened, there were some major pre-existing faults in the continental crust of North America, eastern North America, and those faults reactivated, and along those faults, the crust literally stretched and slid toward the ocean. And as part of that sliding, these sedimentary basins opened up, and we call them Triassic basins. And here I am in the Scottsville Triassic Basin, and one of the distinctive rock types in Triassic basins is red sandstone. And you can see this rock has sort of a maroonish color to it, but also if you look closely in this rock, there's a lot of these green lichens on here. You have to try to ignore them, but this rock is, it's not just red, it's actually red and green. The red part of the rock here is red sandstone. It's a fine-grained sandstone, quite well cemented, but if you look carefully and ignore the bright green lichens, you'll see some of these other sort of a darker green angular pebble. This is a pebble of greenstone, probably the Catoctin greenstone that we find up in the Blue Ridge Mountains. But this rock is in fact a conglomerate. It's got a sandy matrix sandstone, but it contains all these pebbles and boulders of this Catoctin greenstone. We call it a metabasalt. It's a black igneous rock that turns green under metamorphism, and many, many cobbles and boulders and pebbles of that material have ended up here in the western edge of the Scottsville Triassic Basin. Here's another look at a different part of this outcrop, and you can really see here these angular pebbles of greenstone in this red sandy matrix. So what that tells us is as the edge of the continent was collapsing and Pangaea was coming apart, these sedimentary basins formed, and the rocks that were around the edge of those basins were being eroded into the basins. We can tell by their angular nature that they haven't traveled very far, completely unlike the river gravels that we saw in those high terrace deposits that were quite rounded, indicating a fairly long distance of transport. So these basins filled with sediments. They filled with, very often we find conglomerate in the bottom of the basins and around the edges of the basins. And then sandstone, siltstone, finer grained sediment toward the middle and upper parts of the basins. And in the Richmond area, there's quite a bit of evidence that the basin actually had a lake in it. And the lake accumulated a lot of organic debris, and so coal actually formed in the lake that was in the bottom of the Richmond Basin, and that was some of the first coal mining in North America was in a Triassic basin in the Richmond area. And maybe on a later field trip we can visit some sites in the Richmond Basin and see some of these lake deposits. But here we're seeing this red sandstone with these green angular pebbles in it, indicating it was probably some sort of river system or delta quite close to the source of the sediment. Here's something we don't get every day, a gift from the geogods. Someone's done an excavation here along Route 20 north of Scottsville, and they've dug up a bunch of relatively fresh red sandstone. So let's take a look at that rock. You can see the ground here is scattered with these pieces of nice, angular, fairly fresh red sandstone, brick red. I'm going to take my rock hammer and break this one open so we can have a look at that beautiful red Triassic sandstone. You can see there are little white specks in there. Those are feldspar grains, again indicating that this is a relatively immature sediment. Probably hasn't traveled that far. If we were to put our hand lens on those, we'd probably see that those grains are angular as well. But beautiful Triassic red sandstone from the Scottsville Basin.